Obi-Wan uses the Force to push a 65-kilogram battle droid that is initially at rest off a spaceship, hangar deck. Total force of 5.0 times 10 to the 2 newtons is applied for 2 seconds before the battle droid is sent horizontally off the deck. If the spaceship hangar deck is 5.0 times 10 to the 1 meters above the ground, how far does the droid land from the hovering ship? Personally, I am a visual learner, so I always start with drawing the picture of what is going on in the problem. So I drew Obi-Wan Kenobi here and the droid, his distance that he falls, which is what we're looking for, and his motion that he falls. Some things we know is the force of the push, 5.0 times 10 to the 2 newtons for 2 seconds, the mass of the droid, which is 65 kilograms, the height of the spaceship from to the floor, which is 5.0 times 10 to the 1 meters, and we also know that the droid starts at rest. So after I have drawn the picture and I kind of know what's going on, I write down everything that I have. So just like I said, I have the mass of the droid at 65 kilograms, I have the force of the push, the height, the force of the push for the amount of time, and I have the force of I have the velocity and the initial velocity of the droid in the y direction, which is 0.0 meters per second, because we know that he's starting from rest at this point. So the next thing I have to do is I need to make sure that I put a coordinate system on my picture. This is really important because this could either give me less values than I need to solve for or more values. So we always want less values. So any value that we can equal 0, that's what we want to do. So you'll see I'll put it right here. So this is my x and this is my y. So what happens is the droid will fall in the y direction. He moves first in the x direction towards the positive x direction. And then once he falls off the ledge, he's falling down in the y direction. So he'll be moving in the negative y direction. A couple of things that I need to solve the problem are the time the droid takes to fall in seconds in the y direction, and his initial velocity in the x before he falls in the ledge in meters per second, this point right here, and I will need his final value, his final distance the droid lands from spaceship in meters. So now that I've written kind of what I have in my picture and I kind of know what's going on, the next thing that I do is I write down the problem type and kind of what my prediction would be. So the problem type has to do with what kind of problem it is and what potential equations you could be using. So gravitational force I know is going to be involved because of the fall. I know that velocity is going to be involved because of the velocity it takes him to get to this point, and projectile motion because I know that he's moving in a curve, and this is kind of how projectile motion moves. So the next and arguably the hardest part of problems is to figure out the equation that you could be using. So I've already taken the liberty and written a couple here. I'll explain them a little bit. So this is the final position. This would be in meters. We would need our initial position, our velocity initial in the x, multiply that by time plus the acceleration in the x direction, time squared over 2. That's one equation we'll be using. Another is the sum of forces in the x direction equals mass times acceleration in the x direction. This is going to give us another piece of information that we can then put here. Another piece that I'll need is I will need time, but because I don't have enough information here, I can't solve time here. So I'll need to use a different place, use it a different way. So I know that I can use the y final position, pretty much this same equation, but for all my y components. Now I have more information here that I can use because I know a couple of things from the problem. I know that his y initial is his height, where he's starting, how high he is, right? I know that his velocity initial in the y direction is he's initially not moving down, so it's initially 0 after the force of the push. And then the acceleration is something that I have because I know that he's falling, and I can assume that he's on Earth or some sort of gravitational is at play. And so he falls, so I know his acceleration. So with all the components that I know, I can then rework the problem to solve for time, and then plug that piece in. So just as a quick reminder, we are looking for the distance the droid lands from spaceship in meters. Okay, so now that I've taken the liberty to write a couple equations down, the first one I'm going to work with is the sum of forces in the x direction equals mass times acceleration. Forces are really great because we can link kinematics, which are these two equations, through acceleration. So we are given a couple values. We're given the force Obi-Wan pushes and the mass of the droid. So what we're going to do is we're going to cancel our m's, do some algebra, move it over, and we have the acceleration in the x direction, which is great. We're going to use this a little bit later. So the next part is we need to move this equation to get time, because we don't know how much time. This is another variable that's missing in our final equation. So what we have to do is we have to see if we can cancel anything. Now this is really great because this term right here can actually cancel, and I'll tell you why. The velocity initial in the y direction, so when the droid is right here, he's not actually moving down. So we know that that's 0, right? That because I've designated my y-axis right here, his starting position is 0. So what we can do is we can go ahead and cross this whole thing out. So this is great because we want time. So this is just one term that we can just get rid of. Don't need it. So now what we're going to do is we're going to keep going with a little bit of algebra and manipulation. So I know that I can subtract this term and move it over. So minus y initial, the initial position in the y direction. So we have y final minus y initial on one side of the equation. On the other we have at squared over 2. So now we're almost there. We want to get this t by itself. So we're gonna double to get rid of that half right there. The next thing we have is at squared left, 2 times the initial position in the y minus 2 times the final position in the y minus the initial position in the y, divided by a. So now we're left with time squared equals 2 yf minus y initial over a. So now this is super easy. We have time where we want, completely isolated, almost completely isolated, and all of our other variables on the other side. So the last thing we're going to do is we're going to take the square root of both sides. So now we have time equals the square root of 2 times y final minus y initial over a. Now I'll give you kind of a word to the y's here. This is really great because we also know that this thing right here is just like the same thing in change in y. So you can either do two things. You can either keep it y final minus y initial. We know y final is 0. He gets to the end of the bottom of the height and that's it. Or you can just, we just know that his change is his height, right? So you can change it for height, you can change it for change in y, you can keep it here, whatever you want to do, it's all the same. So that's the second equation that we have to work with. Okay, so we're going to keep that. We need that a little bit later. So now what we're going to do is we're going to double check what we have again. Okay, so I've already solved in variable form these two equations, so we already have them boxed in black. Now the last thing we have to do is we really want this value right here, the distance the droid lands from the spaceship in meters, right? So I've taken the liberty to cross these two values out because they actually go to 0, and here's why. The x position, the x initial position, well, he's starting right here. He's moved here, yes, but we don't really care about that part. We care about the fact that he's not moving up until the point he tips, right? So we're right here where he's right before the tip. So that changes to 0. This v, the velocity initial in the x is going to be this acceleration times time. And then that's going to be, this crosses to 0 because he has no acceleration. Okay, so this is what we have as our final. We have the sum of forces in the x direction over the droid's mass, that's one piece of it, times the 2 seconds, times the to get velocity we're going to have to multiply it by time, so times the 2 seconds the droid takes to fall, and then we have time, which is right here. So this is one piece, this piece is right here. Here, I'll show you. So this piece is right here, and this piece is right here, right? So now what we're going to do is we're going to take what we solved here, plug it in. So we have the square root of 2, and I'm going to put the change in y, or the height, whichever you prefer, over a, which is going to be the acceleration due to gravity. Okay, so that's it. There you go. Here's your variable form. I'm going to take some time and erase the board, and then we'll put in our values. Okay, so this is our final variable form. What we're going to do is, now this is a point at the problem-solving equation, or the problem-solving steps, where I like to call plug and chug. So this is really easy because now we have all of our listed values, everything we needed, which now we have, and we can plug it in. So I'm going to do it in black, and I'm going to do sum of push. The F push is the same as sum of forces, right? So this is the first part of it. We know that his force of the push was 5.0 times 10 to the 2 newtons. Your units are really important, so don't forget them. Over mass, which is the mass of the droid, 65 kilograms, times the 2 seconds he pushes him. Okay, so here's your first part. Your second part is your time. So you're going to do the square root of 2. And I have change in y. Remember, just like we said, change in y is the height, is the y final minus y initial. So I'm going to go ahead and just put the height here. 5.0 times 10 to the 1 meters, all over acceleration, 9.8 meters per second squared. Okay, so this is our x final. Yay! Okay, so I'm going to go ahead and plug that into the calculator, and I know that it will be 15.38 meters per second times the time, which is 3.194 seconds. Okay, multiply these two values, and you should get negative 49.4 meters. Okay, so we're gonna pause here for a little bit, and now we've done all of our problem. We have all of our pieces. That's great, but why is our final answer negative? You can't have a negative distance, right? So let me tell you why this makes sense. If you remember, we took the value of here. So gravity usually is facing down, it's directional, right? We know that he's falling down, so technically this value should be negative 9.8 meters per second squared. The reason I didn't do it is because our square root in here, you would get an error. So what I did was I went ahead and I pulled it out. and I put it here because the negative is really just talking about the direction, which is fine because we've designated our y-axis for him to be falling in the negative direction. So this is your final answer, and don't forget your units on all of your terms. Cool. Thanks for watching.